A translation we'll define very non-formally as a slide of a geometric object on a coordinate plane. Is a translation. Sliding it, cut and paste. If you want to think of it even less formally. By sliding in this object, we're going to maintain its original shape and all its features. A transformation that maintains the integrity of the shape, it does not change. The only thing that's changed is its location, not its size, not its angle measures, not anything else. A transformation that does that is called an isometry. So an isometry is just a transformation that maintains the shape and size.
Wait, so are we not doing like a bit?
Correct. What's nice is that all translations, as defined here, must be isometries. So if you can show that what you've done to an object is simply a translation, then it also must be an isometry. It maintains its size and shape. That's all you've done is a translation. Okay. We'll see other examples of isometries in the coming days. For example, rotations on their own are isometries. Reflections on their own are isometries. We'll also see some that are not as well later on. Okay, but in general, isometries are very nice because, again, all they do is they maintain the integrity of the shape. They just move where it's at. Two other vocab words that you encountered a little bit yesterday that I'm going to make sure we're very clear about are pre-image and image. A pre-image is the original object. Pre being before, so this is before we've done anything to it. And the image of the image after transformation is the object after it has been transformed. The image of an object is where it's after. Okay. There's some notation that goes along with each of these. A pre-image, we will label its vertices generally with letters. So, for example, if a point in the pre-image is point A, then its point in the image we'll write is what's called using prime notation. So its image will be A prime. And the prime notation is like an apostrophe that's above and to the right of the letter. So if I had a point here in the original, in the pre-image, its translation or its image will be noted as A prime or new. Prime notation is pretty important. You'll see it a ton in mathematics as it is. You'll see it a lot going forward. Anytime we change or do something new, you'll see prime notation as something that's different. So a lot of this, what's nice is translations is a lot of common sense. So if I ask you to translate the point, say this point 3, 5, 4 units right and 2 units down. If A is 3, 5, then A prime better be what? Well, we'll take A and move it 4 to the right and 2 down. So how would I change, what would I do to this coordinate to move it 4 to the right? Add 4 to which coordinate? The 3, or maybe more generally, the x coordinate. So I'll take the x coordinate and add 4, so I'm going to the right. And I'm going 2 down, so y is talking about up and down, so I'll take the y coordinate, and how do I go down? subtract. So I'll take the y coordinate and subtract 2. Which would tell me the image, or A prime, in this case should be 7, 3, would be the image of this point, A, after the translation. If the original is here, then its prime, or its image is going to be at 7, 3. Something that, so this is kind of a bit of review, but something we've done in the past, and something that we're going to use to what's called verify that a transformation is an isometry, is if it's an isometry, then all the lengths and all the angles will stay the same. Importantly, the lengths are the important part here. So if we verify that all the lengths on the side of a polygon are still the same length, then we're good. Well, in order to find length, we're going to know distance. So we'll just, as a quick reminder, if we want to find the length or the distance of this segment BC, the distance formula, for those of you that don't recall, square root of subtract the x's squared and add that to subtract the y squared. If you don't recall the distance formula. So if I want to find the length of BC, I subtract the x's, subtract the y's, add them, square them, add them together, square root. What's nice is that since we're squaring each of these quantities, it doesn't matter what order you subtract them in, as long as you subtract the x's and subtract the y's. You could screw up the order. You can do x2 minus x1 and y1 minus y2. It does not matter for this formula because no matter what quantity you get in here, you're squaring it, so it's going to become positive. The only thing that switching the order would do would change the sign, but you're squaring it, so it always becomes positive. Anywho, that means that, let's see, in our case, x2 minus x1, so negative 3 minus 1, or 1 minus negative 3 is 4. And if we subtract the y's, we get, 2 minus 5 is negative 3. Then you get negative 4. Okay, what's 4 squared? 16. What's negative 4 squared? Also 16. Same thing here. If you did the other order, you get positive 3. And negative 3 squared is 9. Positive 3 squared is 9. The order is inconsequential. 4 squared is 16. 3 squared is 9. 9 plus 16. We know what 9 plus 16 is up ahead. And what's square root of 25? So BC is 5. Again, if we're unfamiliar with the distance, or at least it's been a while for distance formula, it says essentially if you squared both sides of this formula, you got yourself the Pythagorean theorem. So pretty much the same thing. You can think of these as the legs of a right triangle, and this is the hypotenuse. That's all. Let's do a little graphing. First of all, graph this quadrilateral KLMN with the following vertices: 0, negative 2, 4, 3, 5, 2, 6, negative 1. So let's see. K, 0, negative 2. L is 4, 3, 1, 2, 3, 4, up 3. M is 5, 2. And N is 6, negative 1. Next, find the image of each vertex after this translation rule. xy is transformed to x minus 4, y plus 2. So how am I going to find k prime then? What should k prime be then, applying this rule? Take the x value of any point and subtract 4. Take the y value and add 2. So 0 minus 4 is negative 4. Negative 2 plus 2 is 0. L prime should be, 4 minus 4 is 0. 3 plus 2 is 5. and so on and so forth. I believe we get what? M should be, what, 1, 4, and N prime should be, what, 2, 1. And finally, graph the image with prime notation. So we'll graph all these points. -4, 0. And -4, 0 is A prime. L prime is 0, 5, 0. L prime. M prime is 1, 4, 1, 4. And N prime is 2, 1. And even with my terrible line drawing skills, it still looks as though it's pretty much an isometry. So it's been shifted. Note that every one of these vertices has been moved over 4 and up 2. 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 Huh. Yeah, that kind of looks like a weird 3D box. If I took every one of these and moved it over 4 and up 2, what does it look like if I drew the arrows? What does this look like I actually just drew? Okay. What are these things that I just drew? No, vertices are the points. What are rays that always stop? That's what we thought about. The V word. Vectors. These look as though they're vectors.
That's what I was going for. I said vertices.
They're all this. In fact, they're all the same vector, just with their tail starting at each one of those vertices, not at 0. So what's actually cool is that rather than writing this explicit rule, we could have used what's called a translation vector here. And we'll see that in just a second. But the translation vector for this rule could have been, well, how do we describe each one of these vectors? How could you write it in vector notation? How would you write each one of those things?
-4, 2.
Each one of these vectors goes to the left 4 and up 2. Which is exactly the same as the transformation rule that we had here. So another way to actually write a translation rule is just as what's called a vector form. And it tells you, take each one of those points and go left 4, up 2. Go left 4 and up 2. It's the same way. Let's do the vector rule. If I don't give you the rule, but I give you the pre-image and the image, we could write a rule for sure. We certainly could. We just need to be able to identify where we started and where we ended. That's where the prime notation comes in. That's where the prime notation comes in. So identify on here which one of those two is the original and which one is the image. What's the pre-image and what's the image?
Which one's
This one right here better be the original. Because these vertices all have prime notation. So these are all been changed somehow. So what would be a rule for this? We do an explicit rule. An explicit rule could be written as x comma y is transformed to what? This would be an explicit form of this rule. How can we write the same rule using a vector transformation? Correct? We could just apply the vector 5 3 as well. Would be in vector form. It'll be applied to vector 5, 3. It asks you to verify that this transformation is an isometry. So there's two ways to do this. There's the long and hard way. Well, not hard, but the long and tedious way would be to check that all corresponding sides have the same length. Which means you have to, in this case, apply the distance formula 6 times. You do the easier way. We just said that all translations are isometries. So if you could verify that this rule applies to, this rule is actually the rule that applies to each one of these, you can apply this rule, 3 times? On D, and make sure that it gets you D prime. On F, so it gets you F prime. On E, so it gets you E prime. So apply this rule, say, 3 times. Just simply a matter of checking that this rule actually gives you all the points on our original. That will also verify that this is an isometry.
How do you check that? You just count it out? And you want to
Yeah, what's the coordinate for D? 1, 2, 3, 4. This is -4, -3. So verify that when I apply -4, -3, apply this transformation, that I get D prime, which is supposed to be what? 1, 0. Make sure that when I apply this rule, I get this coordinate.
It's just like a pretty rule check. You don't have to like write anything down
Well,
for that or anything.
If I tell you explicitly to verify that it's an isometry, then you better check that and actually show me that you've checked it. Yes. On the other ones, notice I didn't tell you to verify it.
How do you show that?
D starts here and it goes to D prime, which is here. And make sure that this formula gets you there.
Got it.
E takes you to E prime and the formula gets you there. There's one more example of this. You can, if you want to do this one on your own, you're welcome to. This time I just give you the rule as a vector transformation, as a vector translation, as opposed to the explicit rule. We're going to skip ahead and look at some symmetry ideas. And symmetry ideas in your textbook comes from section 9.6. We're not going to look at explicit formulas for symmetries. We're going to look at them more qualitatively. Line symmetry. If an object displays line symmetry, that means you can draw a line. Can be drawn through an object so that every point on one side is mirrored on the other. If you can draw a line of symmetry, or basically a mirror through, then you're good to go. Then you have what's called line symmetry. And we can actually look at individual lines of symmetry and count how many there happen to be in various objects. Rotational symmetry is similar, but instead of drawing a line and looking for mirrored, what we're going to check for rotational symmetry is that if you can rotate an object less than 360 degrees, it returns to its original form. Then rotational symmetry. If it's possible to rotate it less than a full circle, and it returns to its original form, then you have what's called rotational symmetry. We can just, and if you from there you should be able to describe the angle that you turned it through. Like how many degrees did you have to turn this object for it to get back to its original basic form? So when we look at the information from this section, we're looking at symmetry. We're going to relatively qualitatively, there's not really going to be formulas so much as visualizing and just general problem solving. So if we look through, how many lines of symmetry does this this flower petal seem to have? Yeah, 4. I see 1, 2, 3, 4. Okay, we're going to think more generally here. Yes, these little white things seem to be coming a little bit farther out than the other. The point of this is to get you to see symmetries in generalities, not in. Does it display rotational symmetry? Okay, so it seems to display rotational symmetry. How many degrees we have to rotate this through before it returns to its original shape? Yeah, seemingly 90-degree rotation. I turn this a quarter turn, 90 degrees, and we got a daisy, or whatever the kind of petal this is, not daisy. So we get another flower, the same flower petal comes back to us by rotating it 90 degrees. How about the goat head there? One line of symmetry, seemingly this way, right?
Hey.
No. Right there. Rotational symmetry? Yeah, no. You have to rotate it through a full circle in order to get it back. So, no rotation, one line. The starfish, how many lines of symmetry do you think the starfish has? Okay, let's go a show of fingers.
I don't know.
How many do you think we have? How many lines of symmetry does the starfish seem to have? It's supposed to have 5.
Oh.
This one's a little cut off from my diagram because I miscut and pasted it, apparently. But it's supposed to, yeah, it'll grow back. It should have 1, 2, 3, 4, 5. Does it have rotational symmetry? How far we have to turn it? Joel, how'd you get that? That's a weird number. Joel took 360 and divided it by 5 because it seems as though you could just turn it to the. It seems like we should be able to turn this 5 different times to get it to come back to itself. So he took 360 divided by 5. He got exactly a 72-degree rotation. And Joel's absolutely right. There are 3 more on the bottom you can do on your own.